Welcome to ChemDoctor, and this is the second video presentation on the periodic trend ionization energy. And in this presentation we're going to investigate what happens to the energy required to remove an electron from an atom as we move down any group. Now, like I said in the past presentations, in terms of periodic trends, before you delve into this presentation, you need to watch the videos on attractive forces and how they trend on the periodic table. You need to then watch the presentations on atomic size, and then watch the first video presentation on ionization energy and how it changes moving left to right across the periodic table. And then you finish your learning by watching this video, which is going to specifically deal with what happens to ionization energy as we move down any group on the periodic table. Now, I'm going to go ahead at the beginning here and stipulate what the trend is, and I'm going to abbreviate ionization energy. I'll write this down here. So ionization energy decreases moving down any group. Any group or family, depending on your teacher. They may use the term family for a vertical column of elements, or they may use the term group. Most of the time I think it's group, but there are probably some professors that utilize the term family. All right, so how do we discern what's going on here? And I think of the trends, this is probably, the trends moving down groups are pretty much easier to understand than the ones moving left to right. But let's go ahead and review the relationship we've got with electrons and protons before we get into the nitty-gritty here. So remember that a proton has what we call a positive charge on it, and an electron has a negative charge. Remember that the charge distinction here is arbitrary. We could call one particle blue, we could call one particle red. The whole point is that the two particles have a mutual attraction for one another, which is the same in magnitude. So if one particle is in close proximity to the other particle, then the two particles are attracted and they form a bonding relationship. All right, now what I've done over here on the right side is, as I've provided the schematic which loosely shows the relationship between energy levels where we find the electrons and the protons. And so let's go through and review this quickly. Energy level 1 is the energy level that is closest to where the protons are. The electrons that are in energy level 1 have the lowest potential energy of any of the other electrons, and therefore they are the hardest to remove. In other words, removing energy level 1 electrons will require more ionization energy than removing electrons that are in energy level 2, and so on up the ladder here. All right? So as we move from energy level 1 to energy level 2, and then 3, and then 4, and on the periodic table there are 7 energy levels, it's going to be easier to remove an electron, less energy to remove an electron out of energy level 7 than it will be to remove an electron out of, say, energy level 1. So when we talk about ionization energy relative to periodic trends, how do we figure out what's going on as we move down a group? Well, the thing about this is you've got to remember we have this principle called, or we have this law called Coulomb's law. All right? And Coulomb's law says that the force of attraction, let me go ahead and define this in words. So force of attraction, and we're talking about the force of attraction between a proton and an electron, is proportional. My squiggly means in proportion to charge. And when I say charge, this is going to be the charge relationship between the electrons and the protons divided by the distance squared, the distance in which the electrons and the protons are separated, quantity squared. All right? So in order to figure out what's going on as we move down a group, we have to look at these two principal issues. what's going on with the charge available to attract the electron to the proton, because whatever that force is, in order to remove that electron, you're going to have to put a minimum of that force into the situation. And what do I mean by this? All right, if you think about protons and electrons being magnets, all right, everybody I know on the surface of this planet has played with magnets before. You know, perhaps you've got magnets on your refrigerator, and you realize that in order to pull a magnet off of the refrigerator, you have to exert a certain amount of force to do that. You have to put or burn a certain amount of energy to remove that electron, or excuse me, that magnet from the refrigerator door. So similarly, when we have an electron that is attached to the surface of an atom, if you want to remove that electron, you're going to have to generate at least at minimum an equivalent force for which that electron is being held on the atom in the first place. And in order to get it off there, you're going to have to put a certain amount of energy into the system. All right, the amount of force it takes to remove that electron is going to be dependent on the charge relationship between that electron and the protons, and how far away it is from where the protons are. So now let's take a look at this. First thing we're going to deal with is the charge relationship. All right, and to look at that, we'll start with lithium. And again, we're going to be calculating this thing called Z effective, which is effective nuclear charge. This is, and I'll define it here. I do this in all my presentations, but I'll keep doing it. Z effective is going to be, it's equal to the charge available to exert force on a surface electron. All right, it's the charge available. And what is it equal to? It is equal to the atomic number, because atomic number gives us the number of protons, which is the number of positive charges, minus the core electrons. All right, and the core electrons are the electrons that are between the surface electron and the protons. So to figure out our effective nuclear charge for lithium, first we're going to write the electron configuration. So it's going to be 1s2, 2s1. All right, and again, like I've done in the other presentations, I'm going to circle the core. So here's my core electrons right here. And this guy right here is my surface electron. When we talk about ionization energy, this is the electron that we're talking about that we're going to remove, the energy required to remove that electron. All right? So to find the Z effective for this, we're going to define first the atomic number, which is the number of protons. So it'll be 3 minus, all right, our core electrons, these are the electrons that are sitting between the protons and this outer electron. They're essentially screening this electron from the protons. So we're going to subtract the core electrons from the total protonic charge, and what we get is +1. So this represents the charge that's available to generate force of attraction on this singular electron that's out here in energy level 2. So I'm going to go ahead and put that in here. Our effective nuclear charge for lithium is 1. All right? Now let's take a look at sodium. All right? And moving down the group, all right, sodium's the next element underneath it. And sodium has an atomic number of 11. So the electron configuration for this will be 1s2, 2s2, 2p6, 3s1. All right? And now here's the core, of which there are a total of 10 electrons. All right? And again, this is our surface electron here. So the Z effective for this is going to equal 11, that is the atomic number of sodium, minus the core electrons, which is 10, which gives us +1. So lo and behold, when you look at what's going on here, you can see that the charge available to generate force on the surface electron in a particular group as we move down is constant. So when you come over here to the charge, I'm going to extend that. All right, the charge is not going to change as we move down a group. And I'm going to prove this to you. We need to do potassium really quickly here. We'll do the third one. So K19. All right, configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. All right, and here's my surface electron. All right, and my core is here. All right, if you count them up, we've got a total of 18 electrons here. So your Z effective for potassium is going to be 19 for the atomic number minus 18, and lo and behold, see, our effective nuclear charge is +1, which is what it was for sodium and lithium. And if you continue doing these calculations all the way down this group to francium, this is what you're going to find out. So the bottom line is that moving down any group, your effective nuclear charge, this is the charge that is exerting force on the surface electron, is constant. So the charge value is not changing as we move down any group on the periodic table. Now what we need to do is deal with this distance factor in order to understand why the trend works the way it does. So the first thing I'm going to do, we need to come back over to my diagram, is I'm going to put in the electrons for lithium. So here's its 1s2 electrons. Let's change the color. Here's its 2s1 electron. I'll put an asterisk on it because that is our surface electron. So lithium surface electron is in the 2s shell. I'm going to put that here. Now, let's take a look at what's going to go on with sodium then and identify where its surface electron is. So I'm going to go ahead and put in the electrons for sodium now and change the color. And so here's what we got going on for sodium. All right, and then check this out. Here's its outermost, its surface electron. This would be the one that we're going to remove. So look what's going on here, all right? The surface electron for lithium is in energy level 2. So the distance factor is from here to here. But the surface electron for sodium is between here and here. There is a huge difference in distance between the surface electron for sodium and the surface electron for lithium. If we look at potassium, look, here is the surface electron for potassium. All right, so if I'm going to put in potassium's electrons, I'll change my color again. This is what it's going to look like. All right, and its surface electron is here. And look at the distance difference. All right, we've had another big jump because we're shifting. The surface electrons in this case are shifting to a brand new energy level each time we step down in the group. So the distance factor here is increasing by a large extent. So that means your force of attraction moving down any group is decreasing. All right, and if the force of attraction, right, the force that is pulling on those outer electrons is decreasing down a group, then it becomes progressively easier to remove an electron as we move down any group. It becomes progressively easier to remove an electron as we move down a group. It requires less energy. All right, so let me go ahead quickly here and circle the bottom line. So ionization energy for any particular group decreases as we move down that group or family. And with that, I'm going to go ahead and close the video.